These notes will be over type 2 problems. Projectiles launch horizontally from an unlevel ground. Okay, so the key things here is that it is a horizontal launch, and so there is no like angle of theta. So our v1y is going to be 0 meters per second. So it's basically just like whenever we had our free-falling objects. From the top, if it was just dropped, it had a velocity, initial velocity of 0. Okay, so our vertical velocity is going to be 0. And there's no need to split v1 into components. v1 is just going to equal vx. Okay, so whatever it says the launch speed is, that's your vx. And the maximum height is the launch height, and that is not going to be a calculated component. It's going to be given to you in the actual problem. Okay, so here is a diagram of all the key components of a type 2 problem where it's launched from uneven ground. Okay, so when we draw it, we'll have the maximum height and then the range as well, the dx. Okay, you'll notice that our launch arrow, the green arrow at the top, is our v1, and it is equal to vx. Okay, remember that vx is a constant, so you'll see at the end where the object hits the ground, vx is there as well, and it would be the same value at the top and at the bottom. Our v1y is 0 meters per second because it's not being thrown upwards or downwards. It is just starting off basically being dropped. And then for our v2y, it'll have to be a calculated value. And then using vx and v2y, we would be able to find the final velocity of the object when it hits the ground using Pythagorean theorem, and then finding the angle using tangent of theta. Okay. So our different variables, our horizontal, we have 3 again, and then our vertical, we have 5. So for our horizontal variables, we have delta d of x, which is our range. So how far in the horizontal direction did the object get? Our vx is our horizontal velocity. Remember, it's going to equal our v1, so that'll be given in the original problem. And then our delta t is our elapsed time. For the vertical aspect, we have delta d of y, which is our vertical displacement, and it's going to be negative because we're starting up and then it'll be falling downwards. So our vertical displacement will be negative, and that's going to be given to you in the original problem. Our v1y is 0 meters per second for all problems like these. Our v2y is just our final vertical velocity. Like I said, we'd have to calculate that. Acceleration due to gravity is going to be negative 9.8 meters per second squared. And then our time, our delta t is our time elapsed. Okay, so I kind of talked about some of the problem-solving strategies already whenever I was discussing the diagram. But we're going to be using delta d of y, the change in height, to find the time that it takes to hit the ground. Okay, so then once we have time, we can kind of start solving in the horizontal aspect. The maximum height does not require calculation. It will be given to you in the problem. Okay, and we're going to use Pythagorean theorem and tangent of theta to find final velocity. So with final velocity, we're going to be drawing in the triangle. So here we have our triangle. We're going to be drawing this in and then calculating using Pythagorean theorem and the tangent of theta to find final velocity. Okay, so moving on to the actual example problem. A stunt car is being used in a movie scene. The stunt car will drive off a 74.7 meter high cliff with an initial horizontal speed of 55 kilometers per hour. To film this stunt, the director needs to know how long the car will be in free fall and how far from the base of the cliff the stunt car will land. Also determine the stunt car's final velocity. So there's 3 separate things that we're going to be finding. We will be finding how long the car will be in free fall. That's our time. How far from the base the object or the car will land. So that's going to be our range. And then also the final velocity of the car when it hits the ground. Okay, so that's the 3 things we're going to be finding. So for our strategy, the first thing we need to do is draw a diagram. We also need to convert our V1 into meters per second, because if you notice here, our initial speed is given to us in kilometers per hour. So we have to convert that into meters per second, and then also define the positive and negative directions. So here I define the positive and negative directions as up as being positive and to the right as positive. Okay. I also went ahead and converted my 55 kilometers into meters per second. Okay. Hopefully you remember doing that from earlier chapters. And then I went ahead and I drew in the diagram. Okay, so I wrote in my range. So here is my range. I have my maximum height. Okay, notice that it is negative. Here I drew in my vertical or my horizontal initial speed, which is going to be Vx, which will be the 15.27. Okay, also notice that down here we have Vx. This will also be 15.27 repeating. Okay, I wrote in that my initial velocity is 0 meters per second. For all of these problems, we will have that same situation. Okay, and then I also started to draw in my right triangle at the bottom in order to find V2, our final velocity. Okay, right, the next step we need to do is write out variables in 2 columns. Okay, and so I have our horizontal. The only horizontal one that we have is our initial velocity, which was, when we calculated, 15.27 repeating. And then we have the vertical variables, and so our displacement in the y-axis is negative 74.7 meters. Okay, remember it's negative because it's going to be falling down, so the displacement will be negative. Okay, our initial velocity for y is 0 meters per second. We don't know our final velocity. Acceleration due to gravity is going to be negative 9.8 meters per second squared. And then our delta t, which we don't have. Okay, so since we don't have enough variables in order to solve in the horizontal aspect, we'll go ahead and solve for time using the vertical. Okay, and so we're going to be using this equation to solve for delta t. Okay, so plugging in the information that we know, delta d of y is negative 74.7 equals, our v1y is 0 times delta t plus 1/2 our acceleration, negative 9.8 delta t squared. Okay, so we will know that this is going to cancel out. Okay, it's just going to be 0. And so we're going to be left with negative 74.7 equals negative 4.9 delta t squared. Okay, divide both sides by negative 4.9, and we get 15.2449 equals, so I rounded it to 4 decimal places, delta t squared, so then we have to take the square root of both sides. And we're going to get that t equals 3.90 seconds. Okay, and we're choosing the positive time because negative time does not make sense as far as real life situations. Okay, so our time elapsed that it takes for it to hit the ground is 3.90. Okay, so the next thing we need to find is how far away from the base. So we now have, so that's our range. So we now have our time as 3.90 seconds. All right, so now we can find the delta d of x by using the calculated time and using this equation. Okay, so our Vx is 15.27 repeating. So I'm just going to round it to 4 decimal places. Equals our dx, which we don't know yet, divided by our time, 3.90. Okay, so we're going to multiply both sides by 3.9. And we'll get that d of x equals 59.5834 meters. So this is our range, how far the car was launched in the horizontal direction, so away from the base of the cliff. Okay, the last thing we need to find is final velocity. Okay, so for final velocity, we're using this triangle here. Okay, and so we know v of x is the 15.27 repeating, okay, but we don't know the v2 of y. So we need to calculate the v2 of y in order using the kinematic equations, and then we'll be able to solve for v2 using Pythagorean theorem. To find the final velocity in the y-axis, we're going to use this equation here that's highlighted in purple. Okay, and so our v2y squared is going to be equal to our v1y, which is 0 squared, plus 2 times acceleration, which is 9.8, times our displacement in the y direction, which is negative 74.7. Okay, so this is going to cancel out, and so we're going to be left with v2y squared equals 1,464.12, and then we'll have to take the square root of both sides, and this will be plus or minus, and so we'll get that v2y equals, and we're going to use the negative since it is downward. So negative 38.2638 rounded to 4 decimal places. Okay, so now we have v2y. We can kind of create our right triangle in order to solve for v2. So we know that our vx is the 15.2778. Okay, our vy is the negative, so I have it drawn downward, 38.2638. And then we want to know what is our v2 and the theta. Okay, so we're going to use Pythagorean theorem. So a squared, so 15.2778 squared plus 38.2638 squared equals our v2 squared. All right, so we'll get 1697.5296 equals our V2 squared. We take the square root of both sides, and we'll get that our V2 is 41.2 meters per second. Okay, so now we know the magnitude, we have to just find the direction. So taking the tangent of theta, we're going to have opposite, which is 38.2638, divided by the adjacent, 15.2778. Okay, so solving for theta, it's going to be the inverse tangent of the 38.2638 divided by 15.2778. Okay, so once we calculate that, we should get that our angle is 68.2344, rounded to 4 decimal places. And so for our answer, we just have to put the magnitude and direction together. So we'll have 41.2 meters per second, and it's 68 degrees below the horizon. Okay, you could have put the whole decimal there. I just rounded it to the nearest degree.